Hi, this is the Science Chef. In this video, we're learning about electronic configuration and its relationship with the periodic table. Matter exists in three particulate nature: atoms, molecules, and ions. An atom is the smallest particle of an element that can take part in a chemical reaction. It is made up of three subatomic particles: protons, neutrons, and electrons. While the protons and neutrons are found in the nucleus of the atom, the electrons revolve round the nucleus in electron shells or orbits. Electronic configuration is simply the arrangement of electrons in an atom. In other words, it is the way electrons are arranged around the nucleus of an atom of an element. Electronic configuration can also be called electron distribution. In writing the electronic configuration of an element, we need to know the maximum number of electrons that can be accommodated in a given shell or energy level by using the formula 2n squared, where n is the shell number or main energy level. The electron distribution of the atom of an element can be represented in two ways, namely the shell or KLMN notation and the quantum number or SPDF notation. In this lesson, our focus shall be on the KLMN notation. The table on the screen shows the maximum number of electrons that can be found in each electron shell or energy level. Shell K or energy level 1, which is the nearest to the nucleus, can hold only 2 electrons, while shell L or energy level 2 can accommodate a maximum of 8 electrons. Shell M holds a maximum of 18 electrons, while shell N will accommodate 32 electrons, etc. Let's now look at the electron distribution of the first 20 elements based on the KLMN notation. Hydrogen with 1 shell and 1 electron has a configuration of 1. Helium with 1 shell and 2 electrons has a configuration of 2. This completes the maximum number of electrons in energy level 1. Hence, the third electron will move to the next shell or energy level, which is 2, which makes lithium with 3 electrons to have an electronic configuration of 2, 1. Similarly, beryllium with atomic number 4 has the configuration 2, 2. Remember, based on the 2n squared rule, the second shell can still accommodate more electrons, unlike the first shell that has a maximum of 2 electrons. Therefore, the fifth electron will still go into the second shell, which makes boron with 5 electrons to have a configuration of 2, 3. So, this trend continues for carbon to neon, which has an electron configuration of 2, 8 from its 10 electrons. At this point, the second shell has been completely filled, so the next electron will move to the third shell as shown in the electron distribution of sodium atom 281. The progressive filling of the third shell continues until it gets to argon, which has 18 electrons, with an electronic configuration of 288. The order of electrons filling becomes interesting as the 19th electron goes into the fourth shell as seen in the electron configuration of potassium without filling up the third shell based on the 2n squared rule. Same with the 20th electron, which gives the electron distribution of calcium with 20 electrons as 2882. If you look at the electronic configuration of helium and neon, you will observe that they have the recommended maximum numbers of electrons, 2 and 8, allowed in their outermost shells. These are called the duplet and octet configurations respectively and account for the stability of these elements. Similarly, if you take a closer look at the electronic configurations of potassium and calcium, it will be observed that the 19th and 20th electrons move to the fourth shell without first of all completing the third shell, thereby violating the 2n squared rule, right? No, not really. It's only that the electrons are only observing what we call the pseudo-octet rule, which is the understanding that the number of electrons in the valence or outermost shell of an atom of an element at any given time cannot be greater than 8. Emphasis is on the outermost or valence shell. Therefore, if the 19th and 20th electrons had gone into shell M, the expected electron distributions of potassium and calcium would have been 2, 8, 9 and 2, 8, 10 based on the 2n squared rule, and this would have violated the pseudo-octet rule. So now that we know how to write the electronic configuration of the first 20 elements, let's now see how we can use the electronic configurations to determine their positions in the periodic table. From the KLMN notation, the count of numbers in a given configuration represents the number of shells present in the atom of an element, and the last number represents the number of electrons in the valence or outermost shell. While the highest shell number represents the period, the number of valence electrons represents the group to which an element belongs. So, for the first 20 elements, hydrogen atom has one shell and one valence electron. Therefore, hydrogen belongs to group 1, period 1. Similarly, lithium with 2 shells and 1 valence electron belongs to group 1, period 2. Beryllium belongs to group 2, period 2, while boron is in group 3, period 2 because it has 3 valence electrons. This trend continues with carbon in group 4 to neon in group 8. Next is sodium atom with 3 shells and 1 valence electron, which places it in group 1 and period 3. This continues for other period 3 elements from magnesium in group 2 to argon in group 8. Then in period 4, we have potassium and calcium located in groups 1 and 2 respectively. Because their atoms each has 4 shells with 1 and 2 valence electrons respectively. If you are observant, you will notice that we skipped helium. This is because helium has only 1 shell and 2 valence electrons. Normally, we would expect it to belong to group 2, period 1, but it actually belongs to group 8, period 1. This is because the only shell that helium has is completely filled with 2 electrons, which is the duplet configuration. And elements with completely filled outermost or valence shells based on a pseudo-octet rule are placed in group 8 of the periodic table and are known as the noble gases. Elements in the same group on the periodic table exhibit similar chemical properties. For instance, the group 1 elements, apart from hydrogen, are called the alkali metals because they react with water to liberate hydrogen gas and form alkali solutions. And the group 7 elements are known as the halogens because they combine with metals to form salts. Conversely, elements in the same period exhibit chemical properties which change from metallic to non-metallic properties as we move from left to right. The number of electrons in the outermost shells of these atoms also increases progressively from left to right. We will discuss the group properties of elements in details in our tutorials on the periodic table. If you learned anything from this video, drop a comment, give us a like, subscribe to our channel. It encourages us to do more. Remember to turn on your notification bell to always stay updated with new uploads. A wise man once said, "A smart man knows what to say, an intelligent man knows how to say it, but a wise man knows when to say it." Stay wise till I see you when I'll see you.